And right now for this kind of the assembled beam, they're going to carry the loading, and for example, for this case, the loading is here. So allow me to just use symbols to derive all the information. And for this case, it's asking to calculate, for example, here is point A, and this is point B. The application here is point C, and this free end is the other end is D. So we're going to calculate the first one is the deflections. At C. The second one is the deflection at E. C is here, and E is here. Okay. To analyze these questions, we can use the superposition principle. The thinking process is this. We simply, the superposition principle is on the way you decompose the system into the simplest one, then such that you can utilize the tables. So naturally, I would say I would decompose into two beams. One beam is the system will become this one, and this is A, and here this is B, and here is E, and plus this one is here. For this case, the tricky part is this. The two systems coupled through this support. So that means from here you can see the thinking is this. Once we have loading applied to C, and the loading will transform or will transfer through the elastic object to point B. So that means you expect at point B here that the action and reaction at point B. So let me say the action is this, and reaction would be here. Okay, so that is, let me call this the reaction force, it's called RB. Okay, that's the action and reaction force happen at the same time, at the same place at the same point of the two different systems. So working like this. So furthermore, with this one, then we'll be able to calculate, this one can be further rewrite into this. So this one has, this is A and B, E. This is the force here, unknown, but we know that will be the force RB here. And then on the top side, this is the support. And we know that this is let me put into this is a simply supported. A simply supported, oh sorry, I forgot one thing here. Here I have a loading, here is F, okay? So here is F. So under this situation, simply you can see I replace this reaction by a constraint, or vice versa, right? Because you can see that is reverse thinking process. If we would have a constraint here, the constraint had a reaction that can be like this. So that means yes.
So why do you put that as a roller now?
The roller here, because for the meaning of the roller is this, or sometimes if that is the very elastic material, if this is any elastic material, once we deform, usually it would have a change in the length as well.
Right, but how do you know you could switch it from a pin to a roller?
For this one, or simply is, as one this is a roller here, then I can fix this one. Otherwise, it would have a free body translations. We would want to prevent that one. So, or you can put into this, you can have a roller here and you fix here.
And then it just correlates with your
yeah, either way, okay. The reason why we have to relax one is usually the beam would have also axial deformation. If we fix both ends here, then that means we're going to introduce an additional axial stress, and which will make things very complicated. So we don't do it. So for this case, we can see this one will be coming to our case. That will be case 4. Okay, so for this one, that'll be case 4. And then for this one, we might be able to utilize, for example, case 1. And this one, we need a little bit derivations, but we can use those things. So for the case 4, so let me write it down here. Yes.
When you have like multiple beams, you can kind of manipulate where you want these cases.
Yes, manipulate where to what you like. So the decomposition won't be unique, as long as you can use those things. So here, let me do this one. So here we decompose into, one is this one. So here is F, and this is our case 4. Okay, so here by action reaction, we know that this is F over 2. This is a reaction F over 2. So therefore, RB equal to this value. Okay, get that numbers translated to here. So for case 1, so here we have is this A, B, E, and this one RB we calculated from here is F over 2. Okay. So now for this case, we can calculate case 4. For case 4, the deformation will be like this. And so here we want to calculate diffraction at C here. So this will be the diffraction, and let me call it YC. YC for this case, okay? So for this case, we can check out from the case 4, that means YC. At the middle, if we look at the information here, that will be minus PL cube 48 EI. And again, the minus simply means downward. So that means here, let me write, this is the magnitude 48 EI, and that is downward equivalent. Okay, so basically the sign indicates is downward movement. Is this the diffraction to our answer here? Let me rewrite this one. Determine the diffraction. This is a diffraction due to the both ends are fixed. But you look at our problem here. End B here is floating. For the case 4, we're assuming the both ends are fixed at the ground. So we have such diffraction. But here you can see this one, for the beam BCE, that's supported at one side, that base is floating. So that floating will introduce a little bit more diffraction to this point at C for this combined system. So we need to calculate what is the floating of that base. So basically here you can imagine is this. This base is floating. And to do the floating, let me do the curving, the curve is this. So this is the original shape. And then if assuming the whole thing is as a straight, and due to the movement of the base floating to move to here, so that means this one will become, before the diffraction, this is a base of the beam. And right now, under this situation, due to the application of the loading to this one, the deformation will be like this. So approximately, this is the value we calculated as a YC here. Let me use the different the color. This one is what we calculated YC here. And this one, this distance is due to the floating, the movement of the base, right? Got it? So this distance is how much? This distance, you can see, if we will be able to say, let me call this is the diffraction, this is the movement, let me call this is called the YA. Let me call the delta A, okay? So in this way, this one will be equal to how much? This one will be equal to 1/2 of the delta A. So in total, the deflection for this assembled beam, in total, this one will be equal to 1/2 of delta A plus the YC here. Okay. And some of you have the questions is about how to interpret this amount, and that is explained by this. And how to determine delta A? Delta A is contributed from the deflection of the lower beam. So that means delta A actually is determined by this point here. Can you see it? No?
That's what probably.
So isn't it the deflection of B?
So the deflection of B is going to cause.
You can see this one, the beam, right now, this is the beam of ABE. And so the action direction, the point B, the RB is to press this beam downward. So that means this is assuming this base is stick, kind of welded to the both system, because this point moving downward, that driving this base moving downward, and that one gives us delta A. Again, this base is floating. The base floating based upon the deflection of this one. Okay, so under these situations, right now we're dealing with this case. For this case, this is clamp, and we apply the force here. So here you can see, right now I try to bend it at the middle way. You can see only in the left portion is under bending, right? And this part is free. There's nothing there. So originally, this part is remain straight. After bending, you can see that part still remains straight, but tilted by the slope. And here I apply the loading. Can you see it? So for this case, we can say the loading part is here. This part is free of loading, so that will be treated as the rigid body tilting. Okay, so in this way, can you see? And this one is L/2. So that means if we only to calculate the deflection due to the loading, which is the left-hand part, so that means here we might utilize the information is this one. This is L/2, and the Young's modulus, the moment of inertia, the loading here is F/2. We utilize this model. For this model, that exactly is our case for this one. Okay. Again, that recognize is from here. We recognize here the right-hand part here is free. It's free of deformation. It will deflect, and again, we call it deflection is vertical movement. But vertical movement is a straight line. We can use a simple geometry to figure out the deflection. So the really things here is the left-hand part, is this part.
Isn't it case 1?
Which one?
That's case one.
Case 1, right? Yes. Yes, sorry, case 1. Okay, so here there's a case 1, case 1. Okay.
So you ignore the rigid part of it
Not yet.
initially.
Yeah. So here, let me say this one is deflected is a curve. Okay. So now we can calculate this part. This part is. Let me do this one. So this is the curve drawing here, and then this amount basically is this amount is delta A. Oh, sorry. Let me change.
Isn't it B?
Can I change symbols? This is a point B here. Let me change symbol. This is delta B. That okay?
Yeah.
Make more sense here. So this is delta B here. So this amount is delta B here. Okay, from here to here. So this is delta B. So from here we can utilize what is delta B, and checking the table. Delta B is, if you look at that table, the formulation is minus P. P is a force. And what is a force? F over 2. And P times L cubed. And what is the L? The L in the table represents the length. And here we take out the length. Okay, we put into the template and divide by 3EI. Okay? Here we plug into the template of whatever we given the information here. For this case, the length equal to L over 2, so put into the template of the length, and here we put into L over 2. Again, the minus meaning downward. So here for these examples, then we'll be able to calculate the summation simply will be equal to this one. Then you simply, would that be okay, allow you to plug in the information. So YC has a magnitude there, and delta B has a magnitude just like this. Okay. And now let me finish this one. Again, right now for this case, we apply the loading at the middle and this clamp. So right now bending over is like this. You can see this part remain as a straight line. And then the straight line will be in the orientation depends on the slope at here. So again, the straight line, this will be remain as a straight line, and that will tilt it, remain as a straight line. That tilt angle will be the same as the slope. So right now I'm drawing here, at this point, we calculate what is the angle here. The angle is a theta. So from case 1, we can calculate the theta. What is the theta? The theta at here, this is the theta, and that is a theta, which means that is a slope here, right? So from here you can see this is a theta, and here, let me call the theta at point B will be equal to minus force and L square, the length square divided by 2EI. And again, the minus meaning clockwise direction. So this is the magnitude of the slope. Once we know the magnitude of the slope, then we just extend it into a straight line. So that means here you should be able to calculate deflection E easily. And how to calculate this one. So this part will be equal to delta B. And this part is, you look at this triangle. For this triangle, we know this theta, this angle here, right? So this one will be, this part will be equal to L over 2 times tangent theta B. Again, if you look at this triangle is like this. Okay, and here the theta, in general, theta is very small numbers. And if you plug in the E and I, this will be, the denominator will be huge. So basically here, this can be approximated by L over 2 times theta B. Okay? Again, the issue of this problem is to recognize for the lower portion here, everything on the right hand side in the right range, it remains as a straight line because unloading. And that one from here, we can deduct the information just like this. So for this case, this is the deflection here. That will be equal to delta B plus L over 2 times the magnitude of theta B. Okay, here I would say this is the magnitude. Don't include any minus because minus means we have already taken into the consideration of the direction already. Okay, so let me write it up here. So that will be equal to theta B plus L over 2, and theta B is over 2 times L over 2 squared. Like this. Okay. So that is these questions. And any questions to this?
I'm sorry, what were you trying to show when you have the YC with that, the floating base diagram again?
Yes. This one will look at the, let me draw the whole things here.